Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about Large Language Model, or LLM in short. The topic is based on a tech blog with the title Perturbation Analysis and LLMs. How sensitive are LLMs to their input? Written by a data scientist from Microsoft. You can find the blog link in this episode's description. Throughout this episode, we'll dissect the topic from a quick view on the potential business needs, and then focus on the technology side. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Large language models, or LLMs, have experienced rapid advancement in recent years, with models like ChatGPT and Llama being among the most well-recognized ones. LLMs have demonstrated remarkable capabilities in various natural language processing tasks, including text generation, summarization, and translation. However, LLMs are still in an early stage of adoption, and their nuanced responses to different inputs, perturbations, and contextual variations are still not fully understood. The complexity of LLMs, coupled with their immense parameter sizes and training data, presents challenges in precisely gauging their sensitivity to subtle changes and unexpected inputs. This is something that needs to be addressed or understood further. Perturbation analysis is one important way to introduce small, controlled changes to a system or methodology to evaluate its sensitivity to those alternations. This analytical technique is crucial for understanding the robustness and reliability of a method in various contexts. By systematically perturbing inputs or parameters and observing the corresponding changes in outcomes, researchers and practitioners can uncover how sensitive a method is to fluctuations or unexpected variations. Perturbation analysis has been well used in the industry to understand performance on machine learning models. Taking one example in the context of image classification. Suppose we have an image of a cat, and the model correctly identifies it as a cat with high confidence. Now, to conduct perturbation analysis, we slightly alter the pixels of the image by adding some random noises. After perturbing the image, if the model still confidently classified as a cat, then we can conclude that the model is robust to small changes in the input. However, if the perturbed image is misclassified, or the model's confidence decreases dramatically, it indicates that the model is sensitive to such alterations, and this would highlight potential vulnerabilities or areas for improvements in its robustness. As you can see, given the complexity and expanding adoption of LLMs, this process provides valuable insights into its stability and potentially shed light onto its limitations. and it serves as a lever to understand how LLMs work and perform in real-world applications. Now that we've understood the business problem to solve, let's shift gear and dive into the technology side to learn more about the perturbation analysis. To enable perturbation analysis on LLMs, one needs to decide on two important components. The first one is about how to generate the perturbation, and the second one is about how to measure the difference between the perturbed output and the original ones. Let's look at the first key component, how to generate perturbation. The methodology is pretty straightforward. To replace words in the original input with some variation. One can replace it either with a typo or a synonym. To simulate a typo, the team proposed using query keyword distance as a reference, where letters close in keyboard distance could be randomly swapped. This mimics how a typo would happen in reality. To get a synonym for the word, the team suggested trying out two approaches: replacing a selected word with another random word from the Natural Language Toolkit, or from the top 5 most similar words under global vectors for word representations. With both ways of replacing words into variations, each time a data input is loaded into the LLM, the team randomly flags a maximum of 5 words per data point and performs one of the above operations 3 times. With this approach, the team can generate reasonable perturbations on the inputs, feed them into the LLM model, such as ChatGPT 3.5 Turbo, and collect responses both against the original inputs and the perturbed inputs. Now let's look at the second key component, how to measure the difference between the perturbed output and the original ones. LLMs usually do not generate a single number for most of their tasks. They generate different responses that can be read by a human. While this output is easier to interpret by humans, it is hard to make comparisons between two responses. This requires developing a methodology where it should take inputs of two LLM's responses and output a number as a difference between them. The author proposed two different functions to achieve this objective. The first one is called cosine similarity, which projects the responses into a text embedding that can capture the semantic meaning of the text. Since the text embedding is a high-dimensional numerical vector, this would make similarity comparison between two embeddings as easily done as measuring their cosine similarity. The second function used to understand LLM response differences is called intersection over origin, or IOO, which measures the number of sequential characters that are shared between a string and a reference string divided by the total number of characters in the reference string. For example, if the reference string is "I like to eat chocolate cake," and the string to be compared is "I love to eat chocolate cake," which has 6 words in total. Their interaction part includes to eat chocolate cake, which is 4 out of 6 intersection words. So in this case, the IOO metric would be calculated as 4 over 6, which equals around 0.67. Also, in this example, as you can see, there is only one word change from like to love. And the semantic meaning of the two sentences is pretty close. So their cosine similarity measure would be pretty high, maybe close to 1. This example also highlights that the two matrices can capture different aspects of the comparison. Cosine similarity captures the semantic meaning or intent behind the string, while IOO, on the other hand, captures differences in the characters used to create the semantic meaning. So, having a high IOO almost always implies that the cosine similarity would also be high. However, having a low IOO still allows for the cosine similarity to be high in certain cases. With both components of the perturbation analysis available, the team conducted the analysis over a very common task used for LLM, summarization. The team chose 3 different datasets sourcing their inputs from different domains. GoodWiki, which covers the domain of general knowledge. PubMed covers the domain primarily focused around biology, medicine, and health science. And ArcSphere, which covers the domain of scientific and mathematical disciplines. For each of the datasets, the team loaded the first 100 data points, conducted the above variations to replacing with typos or synonym on the data perturbation, and then they put them into a simple template called summarize the following content, which serves as a consistent LLM prop. The perturbation result indicates little variation between the 3 datasets. It shows that the response difference in cosine similarity is pretty small. Well, there could be a larger variation in the IOO metric. This means that there is a high variability in the output tokens used, while only a small semantic difference. Although the result may be different for other LLM applications, and there may be other different perturbations not included in this study, the finding is pretty assuring for users to use LLM for the summarization tasks. Now we discussed both the business problem and technical solution. Let's wrap it up. In this episode, we discussed what is a perturbation analysis and how the data science team at Microsoft designed the perturbation analysis to understand the large language model's performance on common tasks. If you enjoyed the content of this episode, please subscribe to the channel, give me a 5-star review, and leave a comment. Your feedback is very appreciated, and I'll see you next week.